In this video, I want to talk about the fundamental theorem of calculus, part 1. We'll do part 2 in a subsequent video. So here we go. This is the theorem. It says, if f of x is continuous on the interval, the closed interval, from a to b, then the function g of x, which is the area function under, so the interval from a to x of, of f of t dt, then this function is continuous on the closed interval from a to b. It is differentiable on at least the open interval from a to b. And I can tell you what the derivative is. The derivative of g, so g prime of x, is f of x. Essentially, g is an antiderivative. This is not part of the theorem, this is just my aside. That is, g of x is an antiderivative of little f, of f. This is going to take some proving here, so let's see what we can do. So, I'm given that g of x is equal to that integral from a to x, f of t dt. And, how do you calculate the derivative of a function? Well, think back to your Calc 1 days. If you got a shortcut rule, you'd use it. If you don't have a shortcut rule, you use the definition of derivative, which is the limit as h goes to 0 of g of x plus h minus g of x all over h. Right? So let's see how that definition applies to this function. So we have the limit as h goes to 0. G of x plus h, well, g of x, whatever you plug in for x, it goes up there. So this must be the integral from a to x plus h of f of t dt minus g of x, which is just the integral from a to x of f of t dt, all divided by h. Now, I want to look at this integral and that integral as a picture. Okay, so I'm going to come back to what this is equal to. Let's draw a picture in here. Here's my function, y equals f of x or f of t, whichever one you want. Here's a, here's x plus h. So this first integral is the integral from a to x plus h underneath this function. So it's this whole thing from here to there. The second integral is the integral from a to x. So just stop right here. So it's this stuff. So that numerator, being the big integral minus the small integral, is just the stuff in between. So I'm going to say this now is equal to the limit as h goes to 0 of just the integral from x to x plus h of f of t dt. And I got to divide the whole thing by h, so I'm just going to multiply by 1 over h here. Okay. Now, Now, we're going to essentially use the squeeze theorem to figure out what this limit is. So from Calc 1, we know that this continuous function f on the closed and bounded interval from x to x plus h must have a maximum and it must have a minimum, right? So I want to let little m be the smallest value of f on the interval from x to x plus h. I'm going to move over a little bit here. Hang on. On x to x plus h. Also, let capital M be the largest value of f on that same interval. That should be closed interval, x to x plus h. Okay. If I didn't know that the function was continuous, this wouldn't necessarily be a valid argument. But I do know it's continuous, and I do know that that interval is finite length, and so it's got to be a maximum, it's got to be a minimum. Okay. So what I have is I have that m is less than or equal to f of t is less than or equal to capital M by one of the properties of integrals. I know that the integral from x to x plus h of f of t dt is sandwiched in between the minimum value times the length of the interval, and the length of the interval is h, and the maximum value and the length of the interval, which is h. So that this integral is somewhere in between this value and that value. The picture is, up here, because I've drawn this as an increasing function, the minimum value is this height here, and the maximum value is the height up there. So there's a rectangle underneath here that's going to be less than the area, and there's a rectangle that goes over the top that's going to be greater than the area. And so this area, so this area is somewhere in between the small height times the width and the big height times the width. Okay. Now I'm going to divide everything by h. H is, well, if h is negative, it's going to turn all of the inequalities around, and still I'll have f sandwiched in, this integral sandwiched in between a couple of things. So for argument's sake, I'm going to assume h is positive. So divide by h, I got m less than or equal to 1 over h times the integral from x to x plus h times f of t dt is less than or equal to m. Okay. Now, look at what happens as h goes to 0. I want to claim that little m and big M, both of them go to something very special. Let's take a look. Right? Little m is the lowest value, the lowest y value on this stretch. Capital M is the biggest y value. Well, if h is getting small, so h is here, at this point the x is staying fixed, but the x plus h is changing. It seems to me that little interval keeps getting, doesn't give you as much room here, and that the lowest value and the highest value are both getting closer to whatever the function value is at x. Right? There's that height right here. Why is this not a pencil? There's this height right here, which would be f of x, right up to that spot. Because that interval is getting really small, the highest value and the lowest value have to be getting close to the value that's always there, that is f of x. Again, if the function weren't continuous, I wouldn't be able to make that argument. But since it is, you can't get away from that. So this is all headed to f of x. So the thing is, as h is going to 0, this is going to f of x. This is going to f of x. So the limit as h goes to 0 of this thing in the middle, 1 over h, times the integral from x to x plus h of f of t dt also has to be f of x. This is the sandwich theorem, right? Both ends go to f of x, so the middle has to be going to f of x. This is what I call the windshield wiper theorem, right? That the function g is giving you area underneath this function f, and it's changing by changing the right-hand endpoint. The left-hand endpoint stays the same, but the right-hand endpoint moves. And so as you move that right-hand endpoint, you're getting more and more area. If this is a positive function, if it were negative, you'd be getting less and less area. But when you say give me g prime, just tell me how fast is the area changing. Well, the area is changing faster if your wiper blade is longer, right? So the wiper blade is short down here and you move over a little bit, you gain some area, but not as much as over here with a taller wiper blade, right? This is the windshield wiper problem, that the rate at which the area is swept out is equal to the length of the wiper blade. It's the height function. The derivative of the area function is the height function. Alternatively put, the antiderivative of the height function is the area function. And we were beginning to suspect that with some of the stuff we were doing the other day, right? That somehow this area calculation is related to antiderivatives, and this is precisely it, right? G of x equal the integral from a to x of f of t dt is not the, but an antiderivative of f of x. What this is saying is that every continuous function has an antiderivative. Not the other way around, right? Not taking derivatives. I mean, you could have continuous functions that didn't have derivatives. The absolute value, for instance, didn't have a derivative at 0, but it was still continuous at 0. But now, antiderivatives are always going to be there. If you've got a continuous function, you got an antiderivative. You just take the area underneath. Let's finish this video with a couple of examples. So here we go. Here's a function. G of x is the integral from 0 to x of the square root of 1 plus t squared divided by sine of t dt. What's the derivative of g? The fundamental theorem of calculus says if you got a function like this, then the derivative is just this function with the x plugged in. So this is just the square root of 1 plus x squared over sine x. The derivative of this area function is just the height function at the value of x that you're using as your right-hand endpoint, right? Here's another one. G of x equals the integral from negative 42, actually I wrote a 7, so 72 to x of t squared plus 3 dt. What's the derivative of g? It's x squared plus 3. The fundamental theorem of calculus says, part 1, says that if you got an area function where the variable is the right-hand endpoint, then just to take the derivative of this function, you just plug the x in for t, and you take the height function with that x plugged in. That's all there is to it.